Title: Do LLMs really adapt to domains? An Ontology Learning Perspective. The paper, Do LLMs Really Adapt to Domains? An Ontology Learning Perspective, by Huu Tan Mai, Cuong Xuan Chu, and Heiko Paulheim, delves into the adaptability of large language models, LLMs, to different domains. The authors approach this question from an ontology learning perspective, examining how LLMs can be fine-tuned for specific domains and whether they truly adapt or simply memorize domain-specific information. The paper begins by discussing the importance of domain adaptation in natural language processing tasks, as LLMs are often trained on large datasets that may not cover all possible domains. The authors argue that understanding how LLMs adapt to new domains is crucial for improving their performance in various applications. The authors then introduce their methodology, which involves fine-tuning pre-trained LLMs on several domain-specific datasets and evaluating their performance on a range of tasks. They use an ontology learning approach to analyze the model's ability to learn and represent domain knowledge, focusing on the changes in the model's internal representations after fine-tuning. The results of the experiments show that while LLMs can improve their performance on domain-specific tasks after fine-tuning, they do not necessarily learn new domain knowledge but rather memorize domain-specific patterns and biases present in the training data. This raises questions about the true adaptability of LLMs and highlights the need for further research into how these models can be improved to better adapt to different domains. In conclusion, the paper provides insights into the limitations of LLMs in terms of domain adaptation and suggests potential avenues for future research aimed at enhancing their adaptability. The findings have implications for the development of more robust and versatile language models that can effectively handle a wide range of domains and tasks. In the realm of artificial intelligence, ontology learning, OL, focuses on automatically identifying terms, types, and axioms from unstructured or structured information sources. This paper discusses the potential of large language models, LLMs, in OL tasks, leveraging their ability to capture the meaning of text and reason about it. LLMs have shown remarkable success in generating text and have been trained with enormous amounts of textual data, making them equipped with common knowledge. Recent studies have demonstrated that LLMs can be viewed as knowledge bases, storing knowledge incorporated in their parameters. LLMs for OL introduces a novel approach to OL using LLMs, providing comprehensive empirical evidence that, although requiring fine-tuning for better performance, LLMs can work as effective ontology learners on specialized datasets. However, there are several challenges, including susceptibility to hallucination and the need for further exploration of their generalizability and adaptability to unknown domains. The paper highlights the importance of studying these aspects to better understand the current limits of LLMs, especially as they become increasingly prominent for domain-specific uses. It also presents examples illustrating the potential of LLMs in identifying taxonomic axioms over text, such as identifying that a macaron is a subclass of confection. The paper emphasizes the potential of LLMs in OL and the need for further research on their limitations and capabilities in this field. The paper investigates the domain adaptability and generalizability of large language models, LLMs, from an ontology learning perspective. It presents comprehensive experiments on popular LLMs, including closed and open-source models, evaluating their performance on relation extraction and taxonomy discovery tasks in both in-domain and across-domain setups. The study creates 3 synthetic datasets by turning domain-specific terms into gibberish, simulating the adaptability of LLMs in unseen domains. The findings suggest that off-the-shelf LLMs have limitations in generalization, especially for tasks that leverage lexical semantics. In-domain fine-tuning improves task-specific performance, and these improvements are transferable to new domains. The paper also reviews related work in ontology learning with LLMs, highlighting recent studies that leverage LLMs for ontology-related tasks such as ontology matching and ontology learning. The paper explores the potential of large language models, LLMs, in ontology learning tasks, focusing on their adaptability to new domains. It emphasizes the importance of domain adaptation and in-context learning for LLMs, as well as their performance in various ontology learning tasks such as taxonomy discovery, lexical entailment, and non-taxonomic relation extraction. The authors provide an overview of existing works that leverage LLMs for ontology learning, including Spires, which uses zero-shot learning to extract relations between concepts in textual corpora, and Moskvoretsky et al.'s work on fine-tuning LLMs for taxonomy discovery in specific domains. They also discuss the role of in-context learning with LLMs, citing examples such as chain-of-thought prompting, symbol tuning, and the impact of semantically unrelated labels on LLM performance. Furthermore, the paper touches upon domain adaptation with LLMs, referencing Wan et al.'s domain adaptation framework for very large language models like GPT-4. This framework addresses the scarcity of domain-specific texts by using an adapt-retrieve-revise process. The paper aims to establish whether domain adaptation would hold in arbitrary domains where the terminology is unknown to the model, emphasizing the need for further empirical evidence on the performance of LLMs in ontology learning tasks across different domains. Large language models, LLMs, have shown remarkable performance in various natural language processing tasks, but their adaptability to specific domains remains a crucial aspect to investigate. From an ontology learning perspective, the authors propose an evaluation pipeline to test the adaptability and generalizability of off-the-shelf LLMs. This pipeline consists of two main steps: corpus preparation and LLMs evaluation. In the corpus preparation step, the authors utilize the English WordNet 2023 edition to generate a parallel corpus of terms and definitions in the form of gibberish, serving as a reference domain-specific setting. This process involves selecting root concepts in the WordNet taxonomy, exploring the graph through hyponymy, derivation, and other relationships across concepts, and propagating gibberish representations and definitions to create a parallel corpus. The evaluation pipeline involves dataset extraction, prompt generation, and inference, followed by evaluation. The authors compare the performance of LLMs on real and gibberish datasets, assessing their ability to adapt to specific domains. This evaluation pipeline is crucial in understanding the adaptability of LLMs to domains, as previous studies have shown that domain adaptive pre-training, DAPT, may improve specific task performance but hurt the ability of LLMs to perform question answering. The authors also discuss related work, including Adapt LLM, which aims to improve the adaptability of LLMs to specific domains. They highlight that the in-context learning ability of LLMs heavily depends on the corpus sources and may emerge by combining multiple corpora, but the domain relevance of the corpus may not be indicative of the few-shot performance of the model. This study provides valuable insights into the adaptability of LLMs to specific domains, emphasizing the need for further research in this area. The evaluation of a large language model, LLM, on relation extraction and taxonomy discovery tasks is presented on two versions of a parallel corpus. The study aims to investigate the effect of fine-tuning on in-domain performance. A unique approach involves generating a domain-specific knowledge graph with gibberish representations to simulate an unseen domain. This process includes concept mining, linking, and gibberish generation. The concept mining uses a breadth-first search algorithm to explore relationships up to a depth of 5. The concept linking establishes dependencies between definitions and other concepts. The gibberish generation transforms concepts into nonsensical representations. The methodology is detailed, with examples provided for clarity. The study's objectives and procedures are clearly outlined, showcasing a rigorous approach to understanding LLM performance in various domains. The adaptation of large language models, LLMs, to different domains is a complex process that can be understood through the lens of ontology learning. A novel approach has been developed to propagate gibberish representations and definitions within a concept graph, providing insights into how LLMs adapt to new domains. This algorithm begins by creating gibberish representations and definitions for concepts with no dependencies. In subsequent steps, it utilizes partially processed concepts to resolve dependencies and generate new gibberish representations and definitions. This process continues until all concepts in the domain have been fully processed. An example involving the concepts sweet, compote, fruit, and dessert illustrates this process. These concepts are processed in sequence, resolving dependencies and creating gibberish representations and definitions as they go. This approach demonstrates how LLMs can effectively adapt to new domains by leveraging internal dependencies within the concept graph. Understanding the relationships between concepts is crucial for improving the performance of LLMs in various domains. This novel approach provides a deeper understanding of how LLMs adapt and learn from different domains, highlighting the importance of ontology learning in natural language processing. The authors propose an off-the-shelf evaluation methodology for assessing the performance of large language models, LLMs, in two lexical semantic tasks: relation extraction and taxonomy discovery. This evaluation involves comparing the performance of LLMs on the original dataset and its gibberish counterpart. In the relation extraction task, the goal is to extract all relations between concepts mentioned in a definition, focusing on hypernymy and holonymy relationships. For instance, given a query concept and its definition, the extracted relations should include subclass and part of relationships. The LLM is prompted to output triples in the form A, R, B, where R is either as a subclass of or as a part of. In the taxonomy discovery task, the goal is to determine whether a concept A is a subclass of concept B. The authors use WordNet hypernymy relations as ground truth and compare the predictions on the real and gibberish datasets. Indirect hypernymy relations obtained through the transitive closure of the relation GWN. Hypernym are also used. Negative examples are produced by corrupting the hypernym once or twice per query. The performance is evaluated using the F1 score, and a drop in performance indicates that the LLM relies on lexical senses rather than textual semantic information. The authors follow general guidelines for prompting LLMs, including returning results in JSON format, using chain of thought (COT) if it improves performance, and using one or few exemplars if it improves performance. The prompts for the relation extraction and taxonomy discovery tasks are constructed using specific templates. This evaluation methodology provides a standardized way to assess the performance of LLMs in lexical semantic tasks, allowing researchers to identify areas where LLMs rely on superficial lexical cues rather than deeper semantic understanding. The paper discusses the adaptation of large language models, LLMs, to domains, focusing on ontology learning. It presents a taxonomy discovery task where LLMs are fine-tuned for hypernymy relation prediction in arbitrary domains and unknown vocabularies. The authors propose an experiment to assess the effect of fine-tuning models on inference performance for this specific task. The experiment involves splitting the dataset into training and testing sets, with half of the concepts and their hypernymy relations used for training. Inverse relations are used as negatives, alongside randomly sampled negatives. The remaining relations are used for testing. The authors use instructive datasets with a prefix prompt, completed using each pair of concepts in the hypernymy dataset. This prompt includes identifying whether the statement is true or false, answering with only one word, true or false. The statement is based on the given concepts and their definitions. This section of the paper aims to verify if fine-tuning improves ontology learning performance in existing domains, as previously verified, and if this statement still holds for arbitrary domains and unknown vocabularies where reasoning is required. The authors introduce three synthetic domain-specific datasets derived from the Open English WordNet, named WN Suites, WN Football, and WN Music. These datasets are designed to evaluate performance variations with domain specificity. Table 1 provides a statistical overview of each dataset, including the number of concepts, hypernymy relationships, exploration depth, and root concepts. The WN Suites dataset comprises 244 concepts with 418 hypernymy relationships and an exploration depth of 5, rooted in concepts such as sweet and sugar. The WN Football dataset contains 937 concepts with 1401 hypernymy relationships and an exploration depth of 5, with root concepts including football, team, offensive, and offensive. The largest dataset, WN Music, has 1366 concepts, 2497 hypernymy relationships, and an exploration depth of 5, with root concepts related to musical instruments. The experimental setup is described, including the models used for evaluation. 4 popular language models are employed in the off-the-shelf evaluation: GPT 3.5, GPT-4, Falcon 40B, and Bloom. The number of parameters for each model is provided in parentheses. The authors also mention that the translator T, used to generate gibberish representations of concepts, is available online. A prefix prompt is provided in listing 1.4, which is used for fine-tuning experiments. The content between curly brackets is formatted for each pair of concepts in the dataset. The evaluation methods for this research involve comparing model predictions against ground truths for both English and gibberish datasets. This includes direct comparison with the original English dataset and the gibberish dataset, as well as evaluating the consistency of predictions on the gibberish dataset using the original dataset as a reference. For the relation extraction task, focusing on hypernymy relationships due to limited annotated holonomy in WordNet, the transitive property of relations is applied to infer additional relationships. In the taxonomy discovery task, predictions that are neither true nor false are ignored. Metrics computed include precision, recall, and F1 score for each model and task configuration across the three settings. The results are examined with respect to the ground truths, acknowledging the limitations of WordNet's annotations, particularly in hypernymy and holonomy relationships. The evaluation of the relation extraction task on the GT, X, versus X setting, where X is either a norgib, is presented in Table 2. The results show a significant performance decrease when replacing real terms with gibberish across all large language models, LLMs. For instance, GPT 3.5 feed-S macro F1 score drops from 0.228 to 0.115 when switching from the real to the gibberish dataset. This trend is observed across all LLMs and datasets, indicating that LLMs struggle with relation extraction, particularly when encountering unknown words. The results align with previous findings that off-the-shelf LLMs are not sufficient for tasks like relation extraction. Large language models, LLMs, are increasingly being used in various domains, particularly for ontology learning tasks such as taxonomy discovery and relation extraction. This page presents a comparative analysis of several LLMs, including GPT 3.5, GPT-4, Falcon 40B, Llama 213B, and Zephyr 7B beta, to assess their adaptability across different domains. In the taxonomy discovery task, the models were tested in the GT, X, versus X setting, where X represents either a norgib. The results showed that GPT 3.5 and GPT-4 performed well across all domains, with high precision, recall, and F1 scores. However, the other models' performance varied significantly between domains. For the relation extraction task, the models were evaluated in the ENVS versus GIB setting. This task involves identifying hypernymy and holonomy relations. The results indicated a general performance drop for all models, suggesting that LLMs struggle with unseen words during training. Notably, the prediction alignment was very low, indicating that the models failed to produce analogous outputs from analogous inputs. These findings suggest that LLMs do not reason over semantic relationships effectively. Instead, they heavily rely on the lexical sense and frame of a token. This limitation is critical for ontology learning in arbitrary domains, where hypernymy relationships must be retrieved for unknown concepts or new concepts with different meanings. Overall, this page highlights the challenges faced by LLMs in adapting to new domains and underscores the need for further research to improve their reasoning abilities over semantic relationships. The paper discusses the performance of large language models, LLMs, in open domain question answering tasks, focusing on their ability to adapt to new domains and tasks. The authors present a taxonomy discovery task, where the goal is to determine if a given concept A is a subclass of concept B. They use various LLMs such as GPT 3.5, GPT-4, Falcon 40B, Llama 213B, and Zephyr 7B beta for this task. The results from Table 5 show that the LLMs perform poorly in the taxonomy discovery task, especially when dealing with arbitrary domains. This suggests that off-the-shelf LLMs are not suited for open domain learning tasks. To improve the performance of LLMs, the authors conduct a fine-tuning experiment. They use instruction tuning specifically tailored towards taxonomy discovery and train the model on 20 epochs with a batch size of 4 and a learning rate of 310/6. The results of the fine-tuning experiment are reported in Table 7, which shows that fine-tuning drastically improves the task-specific performance of the LLM regardless of the domain and corpus version. For instance, Falcon 7B's F1 score improves up to almost threefold in the real WN music dataset, from 0.327 to 0.874. Although not surprising for real corpora, an improvement on gibberish corpora is non-trivial, as the LLMs show signs of adaptation on gibberish corpora with improved F1 scores. Overall, the paper highlights the limitations of off-the-shelf LLMs in open domain learning tasks and demonstrates the effectiveness of fine-tuning in improving their performance. The authors investigate whether large language models, LLMs, truly adapt to domains by examining their performance on taxonomy discovery tasks in various settings. They fine-tune LLMs on real and gibberish corpora, demonstrating significant improvements in precision, recall, and F1 scores. Notably, the performance on gibberish corpora never matches that of the same model fine-tuned on the real counterpart, suggesting a limitation of adaptation due to reliance on prior semantics. The authors then explored transfer learning, where an LLM trained for taxonomy discovery in one domain is tested on another domain using only gibberish corpora. The results indicate that F1 scores generally increase after transfer, with substantial improvements ranging from 14% to 32%. This suggests that LLMs can adapt to arbitrary domains with effective pre-training. However, precision tends to drop in favor of recall, indicating that fine-tuning makes the LLM more sensitive to syntactic clues of hypernymy relations at the cost of precision. The authors attribute the performance improvements to emerging reasoning capabilities, where the fine-tuned LLM becomes more capable of abstraction and focusing on semantic relationships between concepts rather than the concepts themselves. This is a promising result, as it points towards the possibility of ontology learning on arbitrary domains with LLMs. The authors present the results of their domain transfer experiment using the Zephyr 7B beta model, fine-tuning it on gibberish corpora and evaluating its performance on ontology learning tasks across different domains. Figure 3 displays the precision, recall, and F1 scores for each domain transfer experiment. The experiments involve transferring the model from one domain to another, such as from WN suites to WN suites, WN suites to WN football, and so on. The results show that the model's performance improves after fine-tuning on gibberish data, with F1 scores ranging from 0.504 to 0.740. The authors conclude that large language models do not adapt well to arbitrary domains, relying heavily on priorly learned semantics, lexical senses, and token frames. However, after fine-tuning on gibberish data, LLMs improve at discovering hierarchies, both on the domain they were trained on and other arbitrary domains. This improvement is attributed to the emergence of reasoning with lexical semantics. The authors emphasize the limitations of LLMs in adapting to arbitrary domains and hope their work will inspire future research to leverage reasoning with LLMs for ontology learning. Supplemental material includes generated datasets, source code for generating synthetic datasets, and code for fine-tuning or evaluating LLMs on ontology learning tasks. The page discusses a series of key concepts and methodologies in machine learning, focusing on the development of novel algorithms for data processing. It begins by outlining the limitations of existing techniques and the need for more efficient methods. The text then delves into the design and implementation of a new algorithm, highlighting its technical advantages and potential applications. The section concludes by addressing potential limitations and future directions for research. The paper explores the role of large language models in enhancing and potentially replacing traditional knowledge graphs in ontology engineering. These models have demonstrated capabilities to learn from context and perform lexical semantic tasks, such as extracting hypernymy relations and aligning conversational ontologies. However, they also face limitations, including a lack of common sense and world knowledge, leading to inconsistencies in their outputs. To address these issues, the authors propose using more diverse and representative pre-training corpora. Recent advancements in large language models, like GPT-4 and Llama 2, have shown improved performance in various natural language processing tasks. These models have been fine-tuned for specific applications, such as chatbots and question-answering systems, demonstrating promising results in terms of accuracy and fluency. The paper emphasizes the importance of continued research and development in large language models to fully leverage their potential in ontology engineering and other areas of artificial intelligence. Recent studies have investigated the adaptability of large language models, LLMs, to various domains. One notable work, Emergent Abilities of Large Language Models, by Wei et al., 2022, explores the emergent abilities of LLMs, highlighting their capacity to acquire new skills without explicit training. Another study, Chain of Thought Prompting Elicits Reasoning in Large Language Models, by Wei et al., 2023, demonstrates that chain of thought prompting can effectively elicit reasoning in LLMs, enabling them to generate more coherent and logical responses. Furthermore, symbol tuning improves in-context learning in language models, by Wei et al., 2023, suggests that symbol tuning can significantly enhance in-context learning in LLMs, allowing them to adapt more effectively to new tasks and domains. A comparative study, Larger Language Models Do In-Context Learning Differently, by Wei et al., 2023, investigates the in-context learning abilities of larger LLMs, revealing distinct differences in their learning patterns and capabilities. Lastly, Large Language Models as Common Sense Knowledge for Large-Scale Task Planning, by Zhao et al., 2023, explores the potential of LLMs as a source of common sense knowledge for task planning, demonstrating their versatility in supporting complex decision-making processes. Collectively, these studies underscore the remarkable adaptability and versatility of LLMs, showcasing their ability to generalize across diverse domains and tasks.